Hi students, welcome to Section Engineering Lectures and welcome to a new playlist on the Design of Steel Structures conforming to IS 800 2007. In today's class, we shall see the design of laterally unsupported beams, flexural members, design bending strength subjected to low shear if you solve problem. In the previous class, we have seen the design of laterally supported beams like this, right? In the flexural members, we found out the design bending strength subjected to high shear if you solve problems, right? I hope you enjoyed the discussions there. Then don't forget to click like, share, subscribe to our YouTube channel, right? Now let's see the brief profile of the speaker. That is Dr. D. Rupesh Kumar, obtained my BTech in Civil Engineering from Nagarjuna University in 1994, MTech Section Engineering from JNTU Hyderabad in 2000, PhD Section Engineering from JNTU Hyderabad 2009. Presently, I am working as Professor of Department of Civil Engineering, University College of Engineering, Usman University, Hyderabad, Telangana State. I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate and postgraduate levels. My research areas include reinforced cement concrete design, steel structural design, structural analysis, fine element analysis, earthquake engineering, bridge engineering, structural optimization. I have published 45 research papers in international as well as national journals and organized 3 international as well as national 3 international conferences and 11 national conferences and workshops, attended 43 workshops, visited 2 countries, delivered 13 guest lectures, edited 3 books, supervising 14 PhD scholars and supervised 30 MA theses. Right? I am actively involved in various consultancy works that are offered by the department and completed over 70 design proof checks and 150 designs of the reinforced concrete design, steel, composite, low-rise, high-rise, multi-stored buildings and road and rail bridges. Right? Now let us see what we'll be discussing in today's class, student. However, the other day we have seen elaborately how a beam can be made as a laterally supported beam. Now let us see the ways and means of making a beam as laterally supported. Therefore, if at all the compression flange is embedded in the concrete like this, or if the compression flange is connected by means of the shear studs and connected to the concrete, or if the lateral the bracings are connected to the compression zone like this, right? Or these are the other ways and means, right? Compression flange is embedded in concrete, just now we have seen, right? Either by directly embedded into the concrete or by means of the shear studs, or even if a metal decking is provided by means of the shear studs, or if at all it is welded to the compression zone, or if the wooden decking by means of the joists are provided to the compression flange, then also, right, like this. Or if the straps are angles are connected to the compression flange of the I section, right? However, at the bottom the tension zone strut is already provided, or alternatively the T's may be provided so that the compression flange will not buckle, or to the compression flange what is connected is a purlin may be connected so that this compression flange will not buckle, or to the compression flange a open web joist may be connected so that this buckling of the compression flange may be avoided, or alternatively the purlins or that of the secondary beams may be connected in the compression zone like this, right? Or they may be connected either by means of a seat angle or without seat angle also as appropriated, or alternatively we may be putting the T's which are already welded to the compression zone, and over which we'll be putting the gypsum roof slab, right, like this, right? Or like this, right? Gypsum roof slab. Or alternatively, what we can do is we can use the precast concrete slab which is connected by means of the metal decks, right? Therefore, these are the different ways of achieving the lateral support for the beam, right? Therefore, so that there is a lateral restraint to the compression flange, like this, right? Therefore, if at all any one of these methods is not done then the beam is said to be a laterally unsupported beam, right? Laterally unsupported beam. Therefore, how these laterally unsupported beams can be designed, now let us examine, student, right? I'll show the schematics like wherein now we can see that this beam is laterally supported by the transverse beams, whereas these transverse beams now, because they are not connected to the slab, they are just like a bare frame. Therefore, these are what? Laterally unsupported. Laterally unsupported. Right? All these transverse beams are laterally unsupported, whereas this beam which is connected between the columns, right, is connected by means of these transverse beams in compression zone. Hence, this beam is laterally supported, whereas these transverse beams are laterally unsupported. Fine. And furthermore, if the shear stud is provided in the compression zone, and it is embedded, if it is embedded into the concrete, then the buckling of this compression plane is avoided. That we have just seen. Or this is that example of a building where the compression plane is provided by means of the metal decking, which is provided by means of the shear studs, right? If all they are welded or welded to the compression zone, then and concrete is poured, then obviously the buckling of compression plane is avoided. This we already elaborately seen the other day, right? And the other ways of achieving the same. Let me see these schematics, student. Right? Just bear for a moment. I'll go to the other schematics, right? These are the other schematics wherein just now we have seen this, right? Whereas even if I take this example of an industrial building wherein this beam, which is called the gantry girder beam, right, is laterally unsupported. Now you can see that there is no support, because over this the gantry girder will be moving not only in the longitudinal direction but also in the transverse direction. Therefore, it is laterally unsupported beam. This beam is a gantry girder beam, which is supported on to a corbel which is resting onto a stepped column. Please see, there is a stepped column, right? Even the other day we have seen the designs of the columns as stepped columns, right? Now, these are the other examples of laterally unsupported beams. Now we can see that there is no lateral support to the compression plane, right? This beam, right? Or this beam, any one of these beams, there is no lateral support, right? And this is another example of a laterally unsupported beam, right? Wherein there is no this compression plane is not at all provided by means of any lateral support, Even here also there is no lateral support to this beam. Therefore, these are laterally unsupported beams, right? And now I'm also showing the other examples, right? Wherein this beam, right? Because it is connected to the you please see that here this beam is connected in the compression zone by means of these secondary beams. Therefore this beam is laterally supported, student, right? Whereas these beams, as of now the secondary beams over which there is no lateral restraint, therefore these are laterally unsupported, like this, right? These are laterally unsupported, right? And these are the laterally unsupported beams, right? And furthermore, let us see the other examples, right? The other examples are like this, right? Yes, this beam, this is a beam, right, which is connected without any lateral restraint. Therefore, this is also laterally unsupported, right? And this is another example wherein I do have right just a bare frame just going like this, right? Therefore, there is no lateral restraint to this beam as of now, right? Even there is no lateral restraint to this beam. Therefore, this is also there is no lateral restraint. Therefore, all these are the examples of the laterally unsupported beams. Or this another photograph wherein if I see this main beam which is connected by means of the secondary beam, this is laterally supported, whereas this transverse beam itself is laterally unsupported. Whereas even we can see at the other end, right, that beam itself is not having any lateral support. Therefore, this itself is laterally unsupported as of now. Laterally unsupported, right? Is laterally unsupported, right? Even this laterally unsupported, right? All the end bay beams are laterally unsupported, right? These are the examples. Right? And Now once we examine this, let us see a numeric problem, student, right? In the previous class we have seen the design of a section was given wherein we found out the design bending strength of that problem. The same problem I'll reiterate. However, in today's class we shall see that with respect to the laterally unsupported conditions. Laterally unsupported condition, right? Is how same previous problem data that determine the design bending strength of ISLB 350 at the rate of 486 Newton per meter if the beam is laterally supported. The other day we have seen. However, if it is laterally unsupported, how much is the design bending strength? And what is given is that the design shear force is less than the design shear strength. The unsupported length of the beam is 3 meters. Use Fe410 grade steel. Fe410 grade steel. Therefore, there is a given data, student, right? For Fe410 grade steel, the ultimate strength of the steel is equal to 410 Newton per mole square, and yield stress is equal to 250 megapascals. And from table 5 of IS 800, I would have the partial safety factor for the against yielding. Governed by the yielding, gamma m0 is equal to 1.1, and governed by the ultimate stresses 1.25, gamma m1 is equal to 1.25. And also from the same IS 800 2007, from table 46 of page number 138, right? What are the properties of this IS LB 350 at the rate of 486 Newton per meter? Or even if I go to ISI Structural Engineers Handbook, which is called SP61 1964, table 1, page number 2, table 1, page number 2. Right, let me go to this SP61 at a quicker pace, right? SP61, yes, this is how ISLB 350 at the rate of 49.5 kg per meter. Now I'm just noting down the relevant properties, right? The depth is 350 and breadth of the flange is equal to 165, and thickness of the flange is equal to 11.4 mm, and thickness of the web is equal to, and that of this web is equal to 7.4 mm, and the moment of inertia about the major axis is equal to 13,158.3 centimeter cube, and about the minor axis is equal to 631.9 centimeter cube. Means that multiplied 10 to the power 4 mm to the power 4, and the radius of gyration about the major axis is equal to 14.45 centimeter or 144.5 mm, and about the minor axis is equal to 31.7 mm. These are all the relevant properties governed by the yielding. However, if the section is plastified, then I need to move to IS 800 from page number 138. Let me go to that page number 138, student, right? Wait for a moment, right? So this is how page number 138, ISLB 350 at the rate of 49.5 kg per meter. Just now this right, all the relevant properties are noted down, right? All these properties, right? 11.4, 7. Right? However, what is now only missing here is I shall know what is this. Also we have seen the section modulus of this section ISLB 350 is equal to 7 ZE is equal to 751.9, whereas the plastic section modulus about the major axis is equal to 851.11 centimeter cube. Therefore, from this table I obtained the plastic modulus ZPZ from table 46 of IS 800 2007. Therefore, once I note down this, now what I'll do is, now I'll find out these are the relevant properties, student. Just now made a note of all these relevant properties, right? Next subheading is what is the section classification? Therefore, as per this IS 800 2007 from table 2, page number 18. Let me go to that page number 18, student, right? Of IS 800 page number 18. 18, yes. And then page number 18, therefore limiting width to thickness ratio. However, what we have is a rolled steel beam is given, whereas for outstanding element of a compression flange, for which for a rolled steel section, this B by TF, right? This ratio outstanding means only half, right? Half means this half of this width of the flange by thickness of this flange, right? Thickness of this flange, whether will it buckle like this, right? Therefore, whether all the fibers are yielded or only top fiber has only yielded or all the fibers are yielded, that is how the section classification, right? Classification, right? Therefore, that now we'll examine that if at all that B by TF is less than 9.4 epsilon, then that is a class 1 buckling or plastic. Sorry, the section is plastic. The section is plastic. All the fibers are yielded. All the fibers are yielded in that flange, right? Or if it is greater than 9.4 epsilon and less than 10.5 epsilon, then this is class 2 or semi-compact, means a few of the fibers are yielded but a few are not yielded, right? And if all is greater than 10.5 epsilon and less than 15.7, then this is class 3 or semi-compact, means only if you have yielded at the extreme fiber, all the fibers are yielded but not in the central core, right? That is the meaning of these plastic, compact and semi-compact, right? Similarly for the web also, I do have, right, a web of an IH or box section, right? Generally in the neutral axis is at the mid depth for this symmetric section, therefore in which case D by TW, depth of this web to that of the thickness of this web, if it is less than 84 epsilon, then that is a plastic section, and if it is greater than 84 epsilon and less than 105 epsilon, then that is compact section, and if it is greater than 105 and less than 126 epsilon, then that is semi-compact or class 3 section, right? Once I note down this, now let me find out what is the section. What is the section now? Hence, doing the calculation wherein the epsilon is the stress ratio, wherein I have square root of 250 divided by Fi for the steel is equal to 250, hence that works out say 1. Hence outstand of this flange means this half of this symmetry, right, is equal to B is equal to BF, entire width of this flange, by 2, means only BF by 2, 165 by 2 means this one, right, 82.5 mm, whereas B by thickness of this flange, 82.5 divided by 11.4, it works out as 7.23, which is less than 9.4 epsilon. That indicates that the flange has yielded. The flange has yielded, or it is a plastic section. The flange is a plastic section, right? Now, similarly, let us see whether all the fibers of the web have yielded or not. All the web have yielded or not, right? Therefore, this is D by TW, whereas D we obtained. What is D? Is the depth of the web, right? Excluding that of the thickness of the flange, as well as the root radius, Therefore, that now works out say H minus 2 times the thickness, of the flange at the top and bottom, and root radius at top and bottom. Therefore, that works out say 350 minus 2 multiplied by 11.4 plus 16, or say 295. I'm just recalling that 295 divided by 7.4, it works out as 39.9, which is much less than 84 epsilon. Hence, the entire web has also totally plastified. Already we have seen that entire flange has plastified and web has plastified. Therefore, now we can conclude that the entire this ISLB 350 has plastified. It is a plastic section. Therefore, and furthermore, we can see that D by TW is less than 67 epsilon, However, if I go to this class 8.2.1.1 as per page number 53, let me go to that page number 53, students, right? 53. Yes. Therefore, now the code says that the design bending strength of a section which is not susceptible for web buckling and shear before yielding, D by TW shall less than or equal to 67 times epsilon shall be determined according to 8212. Means here, if at all it is less than 67 times epsilon naught, the code says that you need not check the web for shear buckling like this. You can avoid that. However, we'll say the design problem, right, how it can be done, that check can be excluded. Right? Now, therefore, the conclusion is that shear buckling check need not be done. Next. However, the other day we already seen, if at all it is laterally supported beam, right, that design bending strength worked out to be 205. I'm just skipping off that. However, in today's class we shall see, if at all it is laterally unsupported, then in such a case I need to refer to the codal provision IS 800 class 8.2.2 page number 53. Page number 53. Let me go to those codal specifications at a quicker pace, student, right? Page number 53, right? These are the codal specifications for the laterally supported beam. The other day we already seen MD is equal to beta B ZP Fi divided by gamma m naught, wherein that MD shall be less than 1.2 ZE Fi divided by gamma m naught in case if it is simply supported beam, and it should be 1.5 ZE Fi divided by gamma m naught if at all it is cantilever beam. That is when it is subjected to the low shear, or where the design shear force not exceed 0.6 VD for the laterally supported beams. This was for laterally supported beam, student. Please make a note, right? However, today we are now designing that of the laterally unsupported beam. Therefore, in such a case, right, even this formula is also applicable. Just make a note. That's why I've just gone through that codal specification, right? However, if all it is laterally unsupported, right, now code says that the resistance to torsional buckling need not be checked, right? If the bending is about the minor axis of the section and section is hollow, rectangular, tubular or solid bar, in case major axis bending lambda LT, right, non-slenderness ratio as defined here is less than 0.4, that we'll see, right? However, the design bending strength of the lateral unsupported beams is equal to MD is equal to beta B ZP FD, where beta B is equal to 1 for plastic sections and compact section, and it is equal to the ratio of the elastic section modulus to the plastic section modulus for the semi-compact section, right, where ZP and ZB are the plastic and plastic section modulus and elastic section modulus, and FBD is equal to design bending compressive stress as given in these tables 13A and B, or alternatively it can be obtained using this XLT Fi divided by gamma m naught, where XLT is the bending stress reduction factor, to account for the lateral torsional buckling. Please see this, right, to account for lateral torsional buckling, like this, right, lateral torsional buckling, and it is given by XLT is equal to 1 divided by pi LT plus square root of pi LT square minus lambda LT square, which shall be less than or equal to 1, where pi LT is equal to 0.5 multiplied by 1 plus lambda LT multiplied by alpha LT multiplied by lambda LT minus 0.2 minus plus lambda LT whole square, where alpha LT is an imperfection factor or parameter which is 0.21 for the rolled steel section and is equal to 0.49 for welded steel sections. However, this non-dimensional slenderness ratio lambda LT is given by this square root of beta B ZP Fi divided by gamma MCR. It should be less than or equal to square root of 1.2 ZE multiplied by Fi divided by MCR, or it is equal to also equal to square root of Fi divided by FCRB, where MCR is the elastic critical moment calculated according to this 8.2.2.1, and FCRB is equal to extreme fiber bending compressive stress in the web corresponding to elastic lateral buckling movement as per this class 8.2.2.1. Now we'll see that, right? Next, how to get this MCR, right, elastic lateral torsional buckling movement, which is called this one, right? However, in case of simply supported prismatic members with symmetric cross section, the elastic lateral buckling movement MCR is given by this square root of pi square EIY divided by LLT whole square, that multiplied by GIT plus pi square EIW divided by LLT whole square, that is equal to beta B ZP FCRB. However, FCRB for non-slender rolled steel sections in the above equation is approximately calculated using the values given in the table 14. However, that values which are given in the table 14 are calculated using this formula. FCRB is equal to 1.1 pi square E divided by LLT divided by RY, means slenderness ratio whole square, that multiplied by 1 plus 1 by 20 LLT divided by RY, HF divided by TF whole square, this under root 0.5. However, even instead of using these two, we can alternatively, right, now code says that the simplified equation may be used for prismatic members made up of standard rolled I sections or welded doubly symmetric I sections, right? Using this formula, MCR is equal to pi square EIY HF divided by 2 LLT whole square multiplied by 1 plus 1 by 20 LLT divided by RY divided by HF divided by TF whole square under root, right? Where IT is equal to torsional constant, which is equal to summation of BI TI cube divided by 3 for open sections, and IW is equal to warping constant. IY, RY are the moment of inertia and radius of gyration about weaker axis, right, or minor axis like this, and LLT is the effective length but lateral torsional buckling, right, and HF is the center to center distance between the flanges, and TF is the thickness of this flange, right? And once I examine all these codal specifications, student, and this is the table also. Using this table, we'll find out, even using this simplified formula also, we'll find out the design bending strength of laterally unsupported beam, right? I have just gone through all this codal specification. Sorry, let me see this table 14, student, right? This is of that this table 14, critical stress ratio, right? However, in the problem, while substituting, I'll revisit these table 13 as well as table 14. Just bear for a moment, right? Let me start the calculations then, right? This is the calculations part wherein the laterally unsupported beams. Let me keep this right. Therefore, once I have seen these, right, just now we have seen that LLT is equal to the effective span. However, there is no data given in the problem. I am assuming that the span, it's the given beam itself is a simply supported beam. Therefore, K is equal to 1. Hence, K multiplied by L is equal to 3 meters. Because what are given in the problem is that directly only the section is given, ISLB 350. That much is only given, and the unsupported length is given. There is no other condition given. Therefore, I am assuming it to be simply supported. Therefore, once I assume it has a simply supported, I got K is equal to 1. Therefore, now let me see the other calculations, right? However, for the steel Poisson's ratio mu or nu is equal to 0.3. Therefore, the shear modulus C, notated by C or G or N, is equal to Young's modulus divided by 2 multiplied by 1 plus mu or nu. Substituting the numeric values, Young's modulus of the steel is the standard value is 2 into 10 to the power 5 megapascals. Substituting which, now I'll get that divided by 2 into 1 plus 0.3. It works out to approximately 0.77 10 to the power 5 megapascals, right? And also, just now we have seen this torsional or Saint Venant constant, which is equal to IT, right? To take care of this lateral torsional buckling, student, right? The summation of BI/TI cube divided by 3 for open sections. However, our rolled steel section is an open section. Please make a note, right? It is not a closed section. Therefore, now I do have IT is equal to 2 multiplied by 2 flanges are there with a thickness of 11.4. Therefore, B T cubed. T is equal to 11.4 cubed divided by 3, that of the 2 flanges, right, top and bottom, and 1 web of 350 minus 11.4, because 11.4 has already gone for flanges. That multiplied by T cubed, 7.4 cubed by 3, because when it is subjected to torsion, right, thickness, right, over the thickness, T cubed, 7.4 cubed divided by 3, right. That is, if it all is subjected to torsion, only thicknesses will be there in T cubed, not the breadth, student. Please make a note, right? Therefore, it now works out to 20.8 10 to the power 4 mm to the power 4. And even if I go to this IS 800 class Annex E 0.1.2, page number 129. Let me go to that Annex. Page number 129, student, right? 129. Yes, and then in Annex E, right, where now I would have this warping constant given by this, right, 1 minus beta f multiplied by beta f IY HY square for I sections, monosymmetric about weak axis. Therefore, now I would have this formula wherein it is equal to 0 for angles T's narrow rectangle sections and approximately for hollow sections, whereas this beta f is equal to IFC divided by IFC plus IFT, where IFC and IFT are the moment of inertia of the compression and tension flange respectively about the minor axis, please make a note. Therefore I just noted down this. Therefore once I see this codal specification now, noted this formula warping constant was is given by this IW is equal to 1 minus beta f equal to IY hy square for I section, and BF, that constant is equal to. However, please see that this section is symmetric about the major axis, right, as well as the minor axis. Therefore, because it is symmetric about major axis, therefore the moment of inertia of the compression flange itself is numerically equal to that of the tension flange. Means the even substituting that, now I'll get that numerator is equal to IFC, the denominator is equal to 2 times IFC. Therefore it now works out BF is equal to beta F is equal to 0.5, and also the center to center distance between the flanges is equal to 350 minus this thickness of the flange, or say 338.6 mm. Substituting this, now I'll get this IW, the moment of inertia for this torsion, right, or torsional constant, moment of inertia against this torsion is equal to IW is equal to 1 minus 0.5 multiplied by, because now beta F is equal to 0.5 multiplied by 0.5 multiplied by this 631.9, because now this is HF is equal to, this HF is equal to 338.6 whole square, student, that multiplied by IY, moment of inertia about the minor axis, is equal to 631 from the data what you have noted down, right? This is 631, this one IYY is equal to 631.9 10 to the power 4. Therefore if I calculate, the result will work out, say a value IW is equal to 1.81 10 to the power 11 mm to the power 4, right? Once I get this IW, just now we have seen this formula, elastic lateral buckling moment, MCR is equal to square root of pi square EIY divided by LLT whole square multiplied by GIT plus pi square EIW divided by LLT whole square. Now I'll substitute each of these numeric values. Therefore pi square multiplied by Young's modulus 2 into the power 5, and moment of inertia about minor axis is equal to 631.9 10 to the power 4 divided by the effective length is equal to 3 meters, that multiplied by the shear modulus is equal to 0.77 10 to the power 5, that multiplied by torsional moment of inertia IW is equal to 1 sorry student, right, this is equal to IT, I'm sorry, right, IT is equal to 20 into 20.8 to the power 4, right, multiplied by pi square multiplied by Young's modulus 2 into the power 5 of the steel multiplied by IW is equal to 1.81 10 to the power 11, that divided by LLT, effective length is equal to 3 meter whole square, this under root, this entire value under root. Therefore it now works out, now I'll divide with 10 to the power, I'll get in terms of Newton mm, now I'll divide with 10 to the power 6, so that I'll get 277.8 kilonewton meter, right? Therefore, and however alternatively even we can find out this MCR value using this simplified formula also, right? This however this is one alternative, student, right? This is alternative 2. What now I'm doing is alternative 2, wherein MCR is equal to, right, pi square EIY HF divided by 2LT, right, this value, right, alternatively, right, that square root of 1 plus 1 by 20 LLT divided by RY divided by HF divided by TF whole square under root, right? Therefore if I substitute that into this simplified formula, now I am having pi square E is equal to 2 into the power 5, and IY is equal to 631.9 to the power 4, and HF, just now we have seen that 350 minus 11.4 whole square, right, that multiplied by 2 multiplied by LLT 3000 whole square multiplied by under root, this under value is under root 1 plus 1 by 20, 3000 divided by 31.7 divided by 350 minus 11.4 divided by 11.4 whole square, or say that divided by 10 to the power 6 will now work out, say 288.09 kilonewton meter. Therefore in the previous case I got using those above calculations, I got 270 8 approximately. Now I got approximately 288 here and there. Almost both are the same here and there. There's no much difference, right? This is alternative 2 student, right? Alternative 2, right? And even alternatively, I can find out using the third alternative, right? What I can do that even this is the alternative 3, right? Whereas this non-dimensional slenderness ratio lambda LT lambda right, sorry, I'll see the other alternatives also. Now let me see uh, let me see this non-dimensional slenderness ratio lambda LT is equal to square root of beta B Z P Z Fi divided by MCR. Therefore substituting the values beta B, because it is totally plastified section, therefore beta B is equal to 1 and ZPZ is equal to 851.11 10 to the power 3, because it is a plastic section modulus multiplied by Fi 250 divided by MCR. Now instead of taking this 288, I am taking using this previous calculations 277.8 10 to the power 6. It works out say 0.8751. However, it should be greater than 0.4. Yes, okay. Hence, the effect of the lateral torsional buckling must be considered. If at all this is greater than 0.4, if at all lambda LT is equal to greater than 0.4, the code says that the effect of the lateral torsional buckling must be considered. However, for rolled steel section, the imperfection factor lambda LT is equal to 0.21. It is equal to 0.1. Let me go to that IS. Let us see that formula, student, right? Let me go to this codal specifications. Codal specifications from page number 53. From page number 53, then I have this. Right? Let me go to this page number 53. Yes, 53. Yes, I'm there in page number 53. Therefore, now as per this, I do have, right? Whereas now we can see alpha LT is equal to imperfection factor is equal to 0.21 for rolled steel sections. Right? Therefore, now I am substituting that 0.21, right, as well as I just obtained lambda LT as 0.871. Therefore, pi LT is equal to 0.5 multiplied by 1 plus 0.21 plus 0.8751 minus 0.2 plus 0.8751 whole square. That now works out say 0.954. Therefore, the bending stress reduction factor XLT is equal to 1 divided by pi LT plus square root of pi LT square minus lambda LT whole square. Therefore, upon substitution, it works out say 1 divided by 1 plus 0.954 plus square root of 0.954 whole square minus 0.875 whole square, or say 0.7496, means approximately it is that value is equal to 75% approximately. Therefore, the design bending compressive stress FBD is equal to this reduction factor XLT multiplied by Fi multiplied by gamma m naught. Therefore, 0.7496 multiplied by 250 divided by 1.1, it works out 170.36 MPa. Therefore, the design bending strength or capacity MD beta B ZPZ multiplied by FBD is equal to 1 multiplied by 851.11 plastic section modulus multiplied by 10 to the power 3 multiplied by FBD. Just now we obtained 170.36, that divided by 10 to the power 6. It works out say approximately 145 kilonewton meter. Therefore, this is how using the formula MCR as well as this using this reduction factor. This is how first alternative we have seen, right? The alternative one using this formula, right? MCR formula as well as the stress reduction factor formula obtained. I obtained the design bending strength or design movement capacity of this flexural member as approximately 145. Whereas let us see the other alternatives also, student, at a quicker pace, right? This can also be calculated using the tables, right? If I want to just use the tables 13A, 13B as appropriately, then what is the actual slenderness ratio, not non-dimensional slenderness ratio, right, is equal to defined as KL by R. However, KL is equal to 3000 divided by R min. We already seen in the data that R R is equal to radius of gyration about the major axis is 144.5, minor axis is 31.7. Therefore, R min is about the minor axis only. Therefore, substituting which now we'll get the radius of gyration. Radius of gyration is equal to lambda 94.64, and also h by tf is equal to 350 divided by 11.4 is 30.7. Therefore, if I go to this IS 800 2007 table 4 student, page number 57. Let me go to that table for page number 57. Right? Let me go to that page number 57. Yes, I am there in this page number 57, right? Wherein for alpha LT is equal to 0.21. Alpha LT is equal to 0.21, right? For Fi is equal to 250. For Fi is equal to 250, right? This column, for this column, right? Now I do have, right? FCRB value is available there, just now I've shown, right? For different H by TF, right? H by TF 30 and H by TF 35. For slenderness ratio, lambda is equal to 90 and for lambda is equal to 100 for 100, right? From this page number 57. From this page number 57, right? Let me go to that page number 57, right? Just by a moment. Yes. Yes, student, this one, right? This table 14, critical stress, FCRB, elastic critical stress, right? For H by TF. Now I have this H by TF value as a 30 and 35. 30 and 35, lambda is equal to 90, 100, 30, 35. Let me focus on that, right? 30, 35. Yes, this one, right? Therefore, this 30 and 35, these two columns, right? These two columns with the lambda is equal to 90 and 100. Therefore, this is how this row, right? 90 and 100. Therefore, 30 and 35. I am just noting down that FCR is equal to for 30 and lambda is equal to 90. It is a 322.9. For 35 it is 309.3, and for lambda is equal to 100 it is 270.9, and for 35 it is 257.7. Therefore, once I note down this data, therefore this data I have just noted down from that table. Now I'll interpolate. Therefore, for 94.64, means for lambda is equal to 90, for H by TF value is equal to 30, it is 322.9. For lambda is equal to 100, this for H by TF is equal to 30, it is 270.9. Therefore, for 94.64, it is equal to 322.9 minus 322.9 minus 270 divided by 100 multiplied by 4.64. It now works out say 98.77. Like that, if I interpolate for H by TF is equal to 35, even it works out say 285.36. Therefore, just interpolated. Now, once I interpolate, therefore, this is just interpolation I have just shown, right? Now I want to interpolate, whereas I have a value of lambda is equal to 94.64, right? For a value of H by TF is equal to 30.7. Therefore, now I'll do further extrapolation, right? Therefore, FCR, now I'll do, therefore, for H by TF is equal to 30, it is 298.77, and for 35, it is 285.36. That over a difference of 5, therefore over a difference of 0.7, this is how much. Therefore, that now works out FCRB, elastic critical stress, 296.88. Therefore, extrapolation is also done. Therefore, now we'll go to this table 13A, page number 55, for rolled steel section with alpha LT is equal to 0.21, and for Fi is equal to 250. For Fi is equal to 250. Let me see this page number 55, table 13A. That was the previous table, student, right? Yes, this is the 13A, not this one, right? Yes, this table, right? This table 13A, corresponding to design bending compressive stress, corresponding to lateral buckling, right? FBD corresponding to alpha LT is equal to 0.21, for Fi is equal to 250 for 250. Now I already have these values of FCRB. FCRB is equal to now my value is equal to is there in between 300 and 250. Therefore, for 300 it is 163.5 and for 250 it is 152.3. Let me show that, right? 300 and 250. Yes, this is the 300 and 250 for 250, right? This column, right? 300, right? 300, 163.6 and 152.3. Therefore, now I'll interpolate. Therefore, upon interpolation, now I'll get this design bending compressive stress as say 162.8 MPa. Therefore, the design bending strength MD is equal to beta B is equal to 1 plastic section modulus 851.11 10 to the power 3, right? Then multiplied by FBD. Just now I got 162.8 10 to the power divided by 10 to the power 6. It works out say 138.56. In the previous case, I got approximately 145 using that first alternative. Now I got approximately 139. There is a marginal difference. Therefore, there is a using the alternative 2, whereas now I go to the alternative 3. Even if you wish, you can find out using that simplified formula as well as the table 13a, right? Let us see that using this simplified formula, student, right? Elastic critical stress FCRB is equal to 1.1 pi square E divided by LLT by RY whole square multiplied by 1 plus 1 by 20 LLT by RY divided by HF divided by TF whole square under root, right? Upon substitution, 1.1 pi square multiplied by 2 into 2 power 5 divided by 3000 divided by 31.5 whole square plus under root 1 plus 1 by 20, 3000 divided by 31.7 divided by 350 minus 11.4 divided by 11.4 under root. It works out say 297.68 MPa. Therefore, just now we have seen from table 13a how these values for FCRB is equal to 300 and 250, FBD is equal to 163.5 and 152.3 respectively. Therefore, if I interpolate for 297.68, it is how much? Therefore, the design bending compressive stress, I am just interpolating, it is now working out 162.98. Therefore, the design bending strength or moment capacity of the rolled steel section given is equal to MD is 1 multiplied by 851.1 1 10 to the power 3 multiplied by 162.98 divided by 10 to the power 6. This is around 138.71 kilonewton meter. Whereas in the previous in the alternative 2 also I got approximately the same value, right? Therefore, this alternative 2 and alternative 3 both are giving the same because the same table is being used. Please make a note, right? The same table is being used. Therefore, both are giving almost say approximately 138.7 here and there, whereas the first alternative using this reduction factor gave rise to 145 because we are hardly substituting up to the 4th decimal, student, right? Even if you substitute up to say larger decimals, 8 decimal or 16 decimals, almost even this value will also try to converge towards this 138.5 or 7, right? Because I'm just rounding off and taking only up to the 4th decimal. There is a discrepancy in the result, right? There is using all the 3 options, right? All the 3 alternatives we have calculated the design bending strength of a given rolled steel section ISLB, Indian Standard lightweight beam 350 at the rate of 486 Newton per meter. The design bending strength is obtained. That is how the first problem, student. I will not check the other checks because the section was given how much was the moment carrying capacity, right? I hope you enjoyed the discussions what we had in today's class. Therefore, then you click to like, share and subscribe to our YouTube channel. In the next class we shall meet with design of built up beams and compound beams, a few problems. Till then, bye bye students.